Good afternoon, good morning, good time of the day to everyone who is attending the seminar. Welcome to our monthly seminar, which is named Horizons of Science. To those of you who are here for the first time, let me say that the idea of this seminar appeared almost 20 years ago when we decided to have a meeting place where scholars in the field of humanities, of natural sciences, philosophers, theologians meet. And the only one rule is that the one who gives the talk makes the talk in such a way that it is comprehensive and understandable for all attendees. And so the seminar, as I say, exists already in view for almost 20 years. Neither COVID nor the war enforced us to stop the seminar. Now, because of the war, we have the seminar online. And today, I have an honor and a pleasure to present you today's speaker, Dr. Reinhard from University of Linz in Austria. Field of activity of Dr. Reinhard is major field of activity is theoretical physics. He is dealing in his studies in theoretical physics with phase transitions, critical phenomena. He founded and led the group in this field in the Johannes Kepler University in Linz. In his studies, he reached quite important results. I want to mention that some of the results were connected to analysis of critical dynamics in conditions of microgravity, which was experimentally, experiments were done in space shuttle. And for these studies, together with Volker Dom from Germany, he got the Walter Schottky Prize of German Physical Society. He is Doctor Honoris Causa of Institute for Condensed Matter Physics in Lviv for his activities in science and also for his contribution to the development of tight professional relations between physicists in Ukraine and in Austria. This year, he got Golden Doctorate from the University of Vienna, and I can continue this list. Another field of activity, and also I would say very successful and professional, is the history of science, philosophy of science, cultural studies. And it is enough to say that in the first volume of our seminar, Обрії науки, which was published in Lviv quite a time ago, one of the chapters has been written by Reinhard. It is about how do ideas in science appear, how they are concentrated in books, and how do books travel from one library to the other. Another book, I have many books of Reinhard. I am happy to share with you if some of you want to have. I put several of them near me. One of them is comprehensive catalog of library of monastery Kremsmünster in Austria, which has incunabulous very rare books and illustrations and so on. And with all this said, I thank Reinhard that he agreed to give today the talk at our seminar, and the stage is yours. Welcome, Reinhard.
Thank you, Yuri, for this kind introduction. And it's a pleasure for me to tell you something about Richard Kirwan. I suppose that those who did not hear my talk at the ICMP I gave last year in December with the title Kirwan's Thought Not Only on Magnetism have ever heard of Richard Kirwan in her physics education. I came across him after retirement by studying Ernst Ising's thesis. There is a short historical introduction following the path of ideas leading to Ising's model for a ferromagnetic phase in a solid-state system. And Ising starts this path with Richard Kirwan, since Richard Kirwan argued that rotatable atomic magnets constitute magnetic matter, and their interaction keeps them arranged in a similar way as crystals which crystallize out of a solution. This was quite different from what was at the time the current theory, namely that also magnetism is some etheric fluid or something else. So, but Kirwan's contributions to natural science were much broader, and he was from other fields known in Europe. And in this talk, I would like to address the position of Richard Kirwan in the European scientific community. Please, next. Thank you. Let me begin with the stage on which each takes place. It's Europe. And you see over the lifetime of Kirwan, 3 stages of Europe. The stages changed enormously. And all over the years you had in Europe wars. I have a list shown below of some of the wars in Europe. And in addition, also there was the American Revolutionary War. On the right side, you see it. Now, when he was born, you see that Europe had a very disparate structure, but you see the British Empire, so to say, in red on the upper side of the left figure. And also Ireland is red. And then you see the blue France, the French Empire, so to say, and then many different other kingdoms and so on. And you see Russia, the yellow, on the right side of the picture. And then I show you in between, in the midst of the life of Kirwan, how this structure has changed. It has changed a lot. If you look on the right side, you see that in your country, also the Habsburg Empire was there. Lviv belonged there then to the Habsburg Empire. You see a Poland reddish structure, and you also see that the Russian Empire had increased in the north and in the south. And when Kirwan died at the end of his life, 1812, you see the dramatic change through the French Revolution and the Napoleon Wars. And it was just in the year of 1812 when Napoleon went to Moscow to conquer Moscow, and you see this long blue noise in the yellow Russian Empire. Now, the interesting situation is that what I show you is a progress in the next transparencies, the progress scientific persons made in this time. It was a time of war, but the scientists were not at war. Lavoisier said, science are never at war. And that's something which moves us also today, because we are also today have war in Europe. And 2016, the European Science Commissioner, Carlos Moedas, said the same. The science might be in peace while their politics are at war. But the situation now is different. And I would like to point to a contribution which you find from last week in Nature, where an Ukrainian scientist said, science cannot be separated from the political war. And I think this is a very strong statement, because we have to solve such a situation. I think the discussion on scientific nationalism and scientific cosmopolitanism is going on, especially nowadays. And it's important also, I think, for the life of the scientists in times as Richard Kirwan had. I mean, it was not easy for the scientists. It was easy, in fact, to move around. Edward Luttwak, from the Military History in Contemporary Conflict Working Group, said in September 2022, in our 21st century, 18th century war, this is the title of the article, he said, the 18th century war fought by rival European monarchs who could all converse in French with each other. They ended not in the utter exhaustion of the collapsing empires of 1918 or in the infernal destructions of 1945, but instead by diplomatic arrangements, politely negotiated in between card games and balls. And you know the Vienna Congress in 1814. And 18th century winners were more likely to console the losers just short of better luck next time. And in a century in which there was war every single year without exception from 1700 to 1800, he said, if one war ended, another necessarily started, or at least persisted, allowing a next time soon enough. And in addition,
I'm sorry, can I interrupt you? Just do you switch slides, because we see the second slide still?
Yes. No, I do not. I just comment these slides.
Oh, sorry.
These slides show the change in Europe and the wars. And you have a list of the wars. And you have also the American Revolution. But the scientists in all these countries could move around. You have examples like Benjamin Franklin. He went to France and he communicated to have in the war the support of the French. And he could also go to Britain and communicate with the British scientists. And I will show you later. So this situation was quite different, I think, from our time anyway. And I want to now, in these circumstances, I want to show you the life of Richard Kirwan. Please, yes. Richard Kirwan, I said, was born 1733 on the west coast of Ireland near Galway. And he came from a Catholic Irish prominent family which belonged to the tribes of Galway, that were 14 merchant families which dominated the political and commercial and social life. You see his castle, it's existing nowadays. It's a hotel, it was a hotel, and now it's an Airbnb, had some rooms to rent, and you could stay at the hotel. He died 1812 in Dublin, and he lived in Cavendish Row, number 6, which I show a picture from our time, and it's not different from the picture which I have from the 18th century. The difference are the cars and the buses. And in between these time scale, he contributed a lot to the science in Europe, and I will give you a short abstract of his life in the next slide, please. So, before 1715, he went in Galway to an interesting school, the Erasmus Smith School, but because he was a Catholic, he could not start his academic studies in England and or in the British university in Ireland at Trinity College. Due to the penal laws, he had to go to France, and he started his studies in Poitiers. And he also wanted to become a Jesuit, but this he did not succeed then. But the most important thing was he went to Paris in 1754 to 55, and he heard a lecture in chemistry, and I come back to this in the following slides. So he started his chemistry studies, and when his brother died, he went back in 1755 to Ireland, and 1757 he married Anne Blake. In Ireland, he also followed his chemistry studies. He could buy books, he followed the publications, and he wanted to contact Blake, who found the carbon dioxide in Scotland, and he wrote to him about his experiment, but he didn't get an answer. So he could not make a contact to another scientist, and this was very disappointing for him. And so he decided to change his interest, and he wanted to become a barrister at the Irish bar. For this, he had to go to England, or he also went to the continent, to Europe, to study law. But the difficulty was again the penal laws. The penal laws, he had to change his faith. He had to change from Catholic to Protestantic faith. And he did it, and he could become a member of the Irish bar in 1766. But this business he didn't like this. He was a scientist, and therefore he gave this up. And in 1769, he again went to London. He had a large library, one he had lost, and he could afford a new library. He made studies. He also had contact to people, and he proceeded with his science. In 1772, he had two daughters, and he cared for the two daughters, and he came back to Ireland and lived in Dublin nearby his daughters, which went to a French school. And he also was in Gretcastle near Galway, and you see his laboratory on the slide where he was 1773 and where he made his experiments. Then 1777, he again went to London, and with this began his stellar decade, as one of the biographs said when he discussed this period, because this period was the beginning of the in Europe known scientific life. He became member of the Royal Society. He made his first publication, 1780, I come to this point, and 1782 already got the Kepler medal about the work of affinities. And this Kepler medal was at that time something like the Nobel Prize in science. And so you see, he was already very respected because he could communicate with scientists, and they were interested in his work. Now, 10 years after, he went back to Dublin and stayed there until his death. In Dublin, he became 1799 president of the Irish Royal Academy, which he also was a founding member, and I come back to his work in Ireland, which he did for his country. Next slide, please. in order to give a short introduction to his scientific contributions, I just mentioned he was very prominent in chemistry, but he was a supporter of the phlogiston theory. I explain it immediately. Until 1791. I mean, it was the time of the chemical revolution by Lavoisier, and he gave up the phlogiston theory. He also worked then in subfields, so to say, of chemistry, in mineralogy, where he wrote the first British mineralogy book, and he ordered the minerals according to the chemical composition. He also worked in geology, and there he was also on the wrong side, so to say. He was a Neptunist, and he opposed the volcanists. Neptunists believed that all the minerals came out of water after the flood, and it's, so to say, for a physicist, the minerals crystallized out of a solution, whereas the Neptunists said the important thing are the volcanism and the fire and the heat, and the minerals came out of a melt, and so they solidified as a melt, out of a melt. I cannot go in this talk to more details. And he also was interested in meteorology, and he formulated that in order to he was interested in the global climate. In order to have measurements from all the countries, they need a conspiracy and of all nations. They should work together, like the astronomers who already work together to see the Venus when it goes through the sun, in order to calculate the distance from the sun. Please, next. Now, in order, you see, he was already very prominent, and it was said this decade marks a great turning point in the development of the physical science, and Kirwan and other Irish scientists certainly helped the science round the bend. When he was in Ireland, he tried to improve the science in his country. And what was the main point was already said by an Italian physicist in a recent video. It was Massimo Porratti, who said the greatest scientific revolution has not been in the 20th century, but that's been the passage from qualitative to quantitative description of nature. And that was also his point. He said always, you have to do experiments to prove what you predict. This change was experienced and recognized by Kirwan and others, and also applied to meteorology. I already mentioned, you have to measure temperature, air velocity and pressure, and so on. What you had in this time were that men of learning were supposed to form a cosmopolitan republic that translated national rivalries and conflicts. And this is called the Republic of Letters. I show here in a map of Europe people with whom Kirwan was in contact. I cannot go to further details, unfortunately. And also I mentioned Benjamin Franklin and Thompson, or better Rumford, which were in America. And so he had contact to France, to Sweden, to Germany, to all Italy. So he was very well known, and this was also seen by different academies which were built in this time in Europe. And I have given here a list where he became academy and member of institutions. And the red ones are, since he was seen as a British scientist, also seen from those countries like the American and the Academy of Philadelphia or the French Academy. He became member at different times, even those two countries were in war. The important for the exchange of the science and knowledge was also that the people organized in clubs or meetings. For instance, London was important because you had the Royal Society and the Royal Society meetings. But there were other meetings. There was the Lunar Society in Birmingham, and in London an additional chapter coffee house society was built by Kirwan. And these societies collected different members from different fields, scientists, instrument makers, and so on, and they exchanged their knowledge. And also they invited people from other countries. So it was also the time of grand tours. People moved through Europe and visited different universities and different academies and exchanged their knowledge. And also in Ireland then he was member of several societies. I come to this point later. Next slide, please. Next slide, please. Yeah, thank you. So here is the starting point of Kirwan's chemistry knowledge. He visited the lecture in Paris of Gustave Rouelle in the year 1745 to 1755. And it was a time of change in the sense I show you here with three examples. The old alchemistic theory had 4 elements. There are 4 elements: the air, the water, the earth, and the fire. And it had some properties: hot, dry, cold, wet. And all the nature exists out of combinations of this and transformations within this alchemistic theory. And this was changed dramatically in this time. And one of the most important change, for instance, I show you here, is that the air, the element of air, is not an element, but it consists of different gases. And so in different time, several gases of the air were found. So it was Black, 1754, he found carbon dioxide in the air. Then Rutherford, 1772, he found nitrogen. And Scheele, and shortly after Priestley, found oxygen. So it was found that the elements are not really elements. We have different gases and also different compounds. And these compounds react differently when you bring them together. And this was a list of affinities. You have here the signs of elements in the first line. And then you have elements below. And this list should show you which element wants to react with the other one, and the lower it is, the less it wants to react. So this was an information you can learn in the lectures. And here you also see, I show you the lecture notes from a student, and the same from the same year. The lecture notes of Richard Kirwan can be seen in the Irish National Academy Library. Next slide, please. Now I come to the first publication. It was late, it was 70-80, and it was a contribution in the English translation of Scheele's, the founder of Oxygen, book which was called Experiments on Air and Fire. And so you have the contribution of Scheele, but also of other scientists within this book. So to say it was a common, usually we have common papers with more authors. It's also like a common paper with more authors. So you have contribution of Bergman, and you also have a contribution of Kirwan, making his comments to different sections. And Kirwan was invited by his colleague in Britain, Priestley, to contribute to this book. So at this time, it is, you can say, European theoretical chemistry was fundamentally transformed in the late 60s. And he names the author names three chemists: Guidon de Morveau in France, Richard Kirwan in Britain, and Toban Bergman in Sweden. They represented the analytic frontier of affinity chemistry to find out which of the compounds and elements want to react in which way with each other. And what we know now, we can see in the comment from 2006, one of the fundamental territories of chemistry is a chemical bond, the element from which an entire chemical universe is constructed. But at that time, this was not known. Please, next. Here I shown you now the dramatic change from the phlogiston theory to the new chemistry of Lavoisier. What you see in the above figure, you see pupils of Rouelle. As I said, Kirwan was a pupil. He heard the lectures of Rouelle, and you see Morveau, Lavoisier, Berthollet, and others, all are pupils of Rouelle, and they are ordered in time on the left side, and they are ordered with his birth date. So the name is on the scale at the birth date. They are all young people. They are from common age. And what you also see is green connections between the people. These are the connections of the French people we work together, and which people which you see on the right-hand picture. It's Madame Lavoisier, Madame Picardet, Berthollet, Fourcroy, Lavoisier, Morveau. And two others are missing, Laplace and Monge. I come immediately to that. Now, on the lower side, you say, 1787, Kirwan wrote his essay on phlogiston. So where he presented his phlogiston theory. Well, each author had its own idea what phlogiston is, so there was a variety of different systems. And it was important for the progress of chemistry. And it was translated into French. Lavoisier could not read British articles, so he was dependent on the translations. And the two ladies, Madame Lavoisier and Madame Picardet, were translator. They translated into different languages. I do not give the list here, but it was German, and it was also sometimes other languages like Italian and Latin. So there was a whole industry of translations, which also made the communication of science in Europe possible. And Madame Lavoisier also, in her translation, used her chemical knowledge. She was engaged with the chemical experiments her husband made, and she assisted him and contributed to the experiments and also to the translation, finding errors and so on. And this appeared 1 year later, 1788. And again, 1 year later, this translation with the comments of all these green pupils of Rouelle and co-workers of Lavoisier was immediately translated into English. And so one could follow the discussion of the new chemistry. And there was a big fight between the two, the system of the phlogiston people and the system of the anti-phlogiston people. And in the year 1791, Kirwan explained that he gave up the phlogiston theory. What was the problem? The problem was that if you burn some material, some metal, then you can burn it with some burning glass, you heat it, and it transforms. And the phlogiston people thought that phlogiston goes out of the element or the compound you burn, goes out into the air. And Lavoisier showed that it's contrary. When you burn, oxygen goes into the metal or into the burning substance, and so to say, it's the reverse progress. And he was right. Oxygen goes together with what you burn and goes out of the air. Maybe I come back to this point later. It's not so easy. So this was the situation. And please, next slide. I want to show you now that not only the connection between scientists in Europe was by exchanging letters or by traveling to them and communicate personally, it also was by lecturing. And one of these lectures was Christoph Lichtenberg in Göttingen. Göttingen, in the Principality of Hanover, which I showed the first pictures, a small red dot, it was under a principality under the King of Great Britain. And George II founded the Göttingen University 1732. And George III in 1760 was King of Great Britain and Ireland and Duke and Prince Elector of this Principality of Hanover. So this university, so to say, belonged to the British Empire, and there were many British students also at the Göttingen University. And one of the teachers there who taught experimental physics was Christoph Lichtenberg. Christoph Lichtenberg was very fond of the British science, and he also traveled on a grand tour to England 1770 and 1774, and he met Duluc, James Watt, Joseph Banks, and Joseph Priestley. So he also knew people which Kirwan knew. And he introduced into his lectures, when he gave these lectures, also experiments within the lecture. Next slide, please. He had sorry, I do not see this next slide. I lost the slide. Do you hear me?
We do hear you, and I also don't have the presentation. Mariana, could you share the presentation, please? Yeah, thank you.
Yeah. Kirwan had a colleague, and this colleague died when he became professor and could give the lectures. And in order that the widow of his colleague could get money, he used this book of the colleague called Ergsleben, and he had several editions of this with comments, and these comments are just historic books to see how science developed. So, but he also named Kirwan in his lecture books. I come back to this point. And in order to show you how both scientists look of the book of nature, I cite Kirwan, which he wrote in the essay on phlogiston 1789. In my opinion, the book of nature should be interpreted like other books, the sense of which must be collected, not from single detached pages, but from an attentive consideration of the whole. So you have, it was also a time where you have developed different disciplines, different types of experiments, different types of fields which you looked at. And so he said that you should bring them together. Quite similarly, Lichtenberg 1794 wrote, "Before God there is only one natural science. Man makes isolated chapters out of this," and had to make them according to his limitations. So one is working in chemistry, one is working in physics. As long as the chapter don't fit together, there is a mistake somewhere, especially in some of them or in all of them. And that was also the problem of the phlogiston theory, because it was, you had experiments which you could say, oh, that is explained by phlogiston theory, other experiments which are clear, explained by Lavoisier's theory, the anti-phlogiston theory. And one of the important points was that if you look at in phlogiston theory, when phlogiston goes away, what is left should be should have less weight. And in the other case, when oxygen comes in the burning process, the burnt thing should be heavier because oxygen combined with them. And so this weighting of the substances was very important. But there was also a theory that phlogiston, it was something strange, could also have negative weight, but maybe I comment it shortly later. So please, next slide. Here I mentioned the textbooks of Lichtenberg, and I show you, I have one of the latest here. It's a thick one of 1800. It was also used in Habsburg countries in Austria and Vienna, and I show you two translations, one in Polish and one in Russian. There is no translation into English or French, but there was the idea to have a translation of this textbook by Volta in Italian, but it was not realized. Next slide, please. Well, what was in the lecture of Lichtenberg? Well, I show you here the titles of the different chapters of the lectures, which was given in Göttingen in experimental physics. The red ones are chapters where works of Kirwan are mentioned. And I go to the most important. There is the effects of attractive forces on liquid bodies. Well, everything was fluid, and this was the affinity. If you have elements and they like to combine, they have an attractive force, so to say. In the chapter about air, he explained how air consists of different gases. Then there was a strange thing. You see, when you burn something, you have heat and cold, and you have light. Also, you have a connection to electricity. I come immediately to that. You have the magnetic force. Kirwan's contribution to that field came too late for the book. And then you have chapters about the structure of the world, the earth in general, something geography, and also meteorology. In every chapter, which I read, you find references to Kirwan's publications. And what the interesting is that you not only have the textbook of Lichtenberg, but we also have the waste book, the Sudelbooks in German, Sudelbücher, where he made comments which were not for public, but which he noted just when he worked in different fields of physics and chemistry. And we also have the notations he made when he was preparing his lectures, and we have lecture books of students. And the most important was a lecture book of Gamow, and the green chapters are out of Gamow's book. And there you can get a picture what of European science was used in the lectures of natural science in Lichtenberg's lectures. He said in one of his books, French chemistry divides all inorganic substances into the following three classes. First, into simple or completely indecomposable substances. Second, into undiscomposed substances, but which cannot decompose or by known means. And third, into composite substances or substances formed from combinations. And to the indecomposable substances, he said you have light, in German Lichtstoff, heat, Wärmestoff, oxygen, nitrogen, hydrogen, electricity, and also later magnetism. These substances are everywhere around the Earth. This was how they saw what had come out of their experiments in this time. And next slide, please. Kirwan followed, of course, the development in chemistry, and in August 6, 1788, Lichtenberg wrote in his booklets, Kirwan now claims that the inflammable pure air, hydrogen, is this phlogiston? He had really excellent supported their opinion, especially in his latest work on phlogiston. And I also believe that the opinion of the real existence of a phlogiston will always hold. At least the experiments must be more decisive than before. But now it has, for some time, under the flags of the Monsieur Lavoisier and Laplace, have spun a sect that completely denies the existence of phlogiston, and one falls to them in droves. The novelty and beauty of the thing adds something to it. But I must say, and that the great merits of this man command respect. You don't have to want to decide on such things, even if for a while you were considered by some to be ignorant, or at least timid. And he characterized what happened. He said, oxygen is minus phlogiston. That's what Lichtenberg liked to do. Next slide, please. And 1791, Kirwan, I also showed it, he refused from phlogiston theory, and he did it in a letter to a friend, to his French friend Morveau, but he also sent this to a German chemist Krell, who published this note and in the Chemischen Annalen, and I read out of this note: although the revolutions in philosophical opinions are of comparatively little importance, yet they often excite some astonishment, especially when they have previously been vigorously defended, as he did. For the same reason, you may perhaps be a little surprised when I confess to you that I have now given up Stahl's system of phlogiston. So this, he declared this. Other people like Priestley or Cavendish and also German chemists did not. They stayed at phlogiston theory over a while. And Lichtenberg noted, it is not surprising that Kirwan had converted. He followed him. His system already contained too much of the others. His phlogiston already has too much of the hydrogen of the others, or it is real. And Gamow said, now chemistry, to which Lichtenberg was wholeheartedly devoted. So Lichtenberg was not completely decided of Lavoisier, Lavoisier's system, but he saw that it is a future, so to say. And in our time, this was judged that if Kirwan was indeed telling the truth about why he did so, and I think there is no reason to doubt this sincerely, this abandonment of phlogiston for the new chemistry is indeed noteworthy. Next slide, please. So I want to point to another European scientist, Alessandro Volta. And now I go very quick because time is becoming late to the transparencies. He started his work also publishing in chemistry, 1776. He was a professor of physics at the Royal School in Como there, and then moved to Pavia and became professor. And he characterized as one of the reformers in Austria, Lombardy in the age of enlightenment. And he had many students in his lectures. And he was also connected to Lichtenberg, and he met them on a grand tour, and he also met Kirwan on a grand tour to England, 1781 and 82. And he was influenced by Richard Kirwan's research on the composition of fixed air and its role in the reduction of metallic calxes. And by Priestley's experiments on the metallic reduction, which lead to oxygen and so on. So he was informed on that, and the important thing is that he then also worked on the connection of chemistry and electricity. Next slide, please. At the beginning of the French Revolution, 1789, there was an important experiment. The Netherlands scientists Troostwijk and Tema made an experiment by putting an electrostatic generator, giving the electric they connected the electric currents into the water, and they made electricity, static electricity, by this electrostatic generator by rubbing. And so they could put electricity into water, and they saw that something is happening, because there were gases produced at the points where the electricity goes to water, and it was hydrogen at one cathode and oxygen at the other, and at the anode. And they, however, did re-spark immediately in water. They came together and again flashed out, and nothing happened. So it was not very easy to separate what I said, hydrogen and oxygen, but they could see that on one side they had hydrogen and on the other they had oxygen. And that was very strange, because Lichtenberg said all electricity that nature produces, like all fire that it produces without our doing, is produced by chemical combination and separation. And so it was very important. And next slide, please. Volta knew Galvani, and there we had natural electricity. And in 1800, Volta presented the pile in London he made. You see below Volta, you see his pile. It was a combination of tin and silver, and in between some wet, so they were separated, the metals, by some wet material, and then he could produce an electric current. And what he did, he put the anode and cathode, what we say today, into the water, and then he could really, as you see here in the experiment shown in a graph which is modern, he could reproduce Troostwijk and Tema's experiment from 1789 very nicely, and he could show that on one side you have hydrogen and on the other side you have oxygen. And you also see that the quantity is different, and this already goes to Dalton and the new, and what you find in the 19th century, to atomic chemistry and Avogadro's laws. So the situation, nevertheless, was Lavoisier chemistry never explained why chemical reactions happened, and phlogiston was later seen to have held the conceptual space that chemical potential energy would fill. On the other hand, phlogiston was even at the time commonly identified with electricity, and could easily have been kept and developed into the concept of free electrons. So this is the opinion of Hasok Chang in his interesting book, Is Water H2O? So this led to a discussion about the chemical revolution and about how you have to judge this scientific, so to say, competition between phlogiston theory and Lavoisier's anti-phlogiston theory. But this was resolved by the electrons, the currents, everything in the 19th century and later. So I hurry now over to the next slides. And I would like to go, next slide, please. Yeah, when Kirwan came back to Ireland, I hurry through it now, he had the maxim, with labor and money, nothing is impossible. And he wanted to improve the situation in Ireland. He was engaged with the founding of the Irish Academy. He was behind the acquisition of the Leschian mineral collection. And the mineral, Ireland could buy it, and it is now in Ireland. He also applied his knowledge in chemistry to manures. So concerning Mr. Kirwan's charming treatise on manures for the economy of farmers, science never appears so beautiful as when applied to the use of human life, nor at any use of engaging as agriculture and domestic economy. That was written by Thomas Jefferson, who also knew this work of Kirwan. And Kirwan also wanted to improve the Irish mines, and he became Inspector General of Her Majesty's Mines in Ireland. And so you see, he wanted not to do only basic science, but also applications and to different fields in agriculture, in mining, and also his meteorology was important for the agriculture. Next slide, please. In order to do so, he also was engaged, he was a member of different social organizations in Dublin, but I only show the names: Dublin Library Society, Irish Academy, and also the Catholic Committee and the Dublin Society of United Irishmen. That was very important for the independence of Ireland. And you see the different occupations of the members. So it was not only scientists, but also people of economists and so on. So next slide, please. Now, in the Irish Rebellion, in the year 1789, Irish wanted to become independent because it was frustrated of lack of reforms. But Kirwan had a general position to improve Ireland. Of course, he was member of the Irishmen, but he was not politically engaged. Next slide, please. He wanted to improve, and therefore he also wanted to bring a new academy to Ireland. An academy like the Mining Academy of Freiberg, he knew from Germany. So Irish scientists were sent to this academy and made contact to the German mineralogist Mohs. And Kirwan planned to invite Mohs and speak with him about the project to create an academy in Ireland. But unfortunately, the director, which was supposed to lead this academy, died, and it never came to this project. Next slide. Morse could not work in Ireland, but Morse could realize this type of academy or mineralogical society in Graz in Austria in 1811. And so we have in Austria, so to say, some exhibition of mineralogs and a museum which was in fact planned for Ireland but never realized. So with this, I want to stop now my talk, and I want to thank first for the possibility to give this talk. I want to thank also all my colleagues who worked with me when I discussed with them, and I would give a special thank to an Irish colleague, the physicist Ralph Kenner. His comments and his interest in this topic kept me going on and following the path now of Richard Kirwan through the science in Europe. So thank you very much.
Thank you very much, Reinhard, for this very big work, very interesting lecture. As far as I know, you are in the course of writing papers on this, and probably it will lead to the book. And I am happy that attendees of this seminar were at the, so to say, at the first steps to this future book, and good luck with this. Are there any questions or comments? I don't see the questions yet. Maybe I put my question. You know, somehow now in 21st century, we are used to the point that science is connected with reductionism. And somehow, at least I am thinking, last century, the century before last, it was always certain field of science devoted to certain feature of nature. And this holistic approach, for me, it is our feature, our very modern feature. Now we are looking holistically on the phenomenon and studying it from very different sides. That's why I was astonished and very pleased to read these sentences. I wrote them down to my booklet when I was listening to your talk by Kirwan and by Lichtenberg, when they say, you know, you have a book of nature and you should not take out certain page and be interested. So in this sense, this holistic approach was always present.
Yes, I would say so. I mean, it was the time of enlightenment was a time of change from to looking at nature as a whole, but in doing science, you have to separate in different fields. And I mean, if I look at this affinity, I mean, we have to know how does chemical elements or chemical compounds are built. You have to find the atomic structure. You have to find the electrons. And now this year we got a Nobel Prize for that. You can look at the electron, what it prefers. And you can look how the compound is built. And it has a name and it is a project. It's now attochemistry, because in attoseconds you can follow the electron. And what do you get? You get medical assistance in looking at the blood elements and finding illness and so on. So what you see on one hand, you go to different deeper levels. On the other hand, you connect different fields. And also in our time, I mean, if you look at complex systems, you have not only to consider how are the units you look at, you have to look how do they interact? And you have to look, why does the interaction change? Why do you have in such systems a development? And so you have to look at the system as a whole. And on the other hand, you have to use the scientific possibilities of the separate fields, of the very specialized fields. I mean, what you do with phonons now, with light, experimentally, how you use it, that's fantastic for me. And it was, at that time, it was a fluid, and electricity was a fluid, and the fluids fluid around. And they said, well, it's within the solid, and it fluids through porous portions like Euler and others had other ideas. So it's this composed picture you should have. And the interesting thing is that even in some years ago, 5 years ago or so, one wrote a paper in astronomy and cosmology on the theory, what would you gain if you assume that also in masses could be negative, like phlogiston? That was very surprising. And it was commented with the phlogiston theory by some readers. So the interesting thing is also, and that's also the nice in Lichtenberg, that you, and the Nobel Prize winners also said this, you have crazy ideas, but they do not realize, but they can improve the going on of an idea. So it's not strange that the people assumed phlogiston could also be negative. Why not?
Yeah.
They didn't know if electricity is positive or negative or both. And they didn't know what magnetism is. And is it also positive and negative? No, it's also always a dipole. It's also an atomic unit. So all these developed in this time, but it was only seen when you go through different stores in nature.
Right.
But you have to combine them. And you have to see what emerges out of some laws if you have many units working together.
Yeah, thank you. Are there some other questions? Yes, please, Yaroslav Bazali.
Yeah, thank you. I guess, do you hear me?
Yes, we do.
Okay, thank you. So one statement that was made that time of Kirwan was a time of enlightenment. And then I think you posed the question of science becoming united at the present time again. And at the same time, if you read many scientists, you would see that a number of them, they have a totally opposite idea. They have an idea that our time is rapidly becoming the time of anti-enlightenment, the time when the ideas of enlightenment are not popular. And so I just wanted to ask Reinhard, your personal opinion. Do you think there is merit in those discussions, and do you take side in them?
So it was a question if my description of the Enlightenment, and there are other descriptions of Enlightenment nowadays, which are called anti-Enlightenment.
I would say the question was about the present day. Do you think it reminds about Enlightenment, or it follows the tradition of Enlightenment, or it doesn't?
Reinhard, your microphone is muted. Please unmute.
So the situation today is, I think, more, I would say, in the sense I cited from Kirwan and Lichtenberg. It's more, again, to use methods and to combine methods of different fields. We apply physics in very different fields, which we thought in former times there are only special methods usable in physics, and not, for instance, in humanity. Or we apply it in economy, or I think chemistry is another example. You can say, well, did Enlightenment find out that chemistry is in fact physics? There are some additional things you should consider, I think, if you look at chemistry. To explain, for instance, all the combination of the atomic level, where the energies come from, and so on, to make these balance laws. So I think I would say it's more such an holistic view, which is usable and successful. Nowadays, I would say it's complex systems. And you have to use in complex systems all foundings of different scientific disciplines.
And again, if I may, when you mentioned that Kirwan also worked in the field of meteorology and mineralogy, right? So it is, for me, again, it resembles modern approach to study of climate.
I mean, so thank you that you mentioned meteorology. I think, so you have astronomy, and it is a cooperation of different methods and different locations. So it is a global action if you make a measurement of the transition of Venus and you want to do something. That was already done in that time. But if you look at the climate change, for instance, I mean, you need an overview over all of the world, and you have to combine chemical processes, you have to combine measurements made, temperature, physical measurements, and so on. So you have to combine many things. You should know something from geology, you should know something of oceanography or so. When I say it, you have to know how behaves our large amount of water. What does the wind if it goes over mountains, and so on. And combining this is possible by combining all the equations and calculating them in computers, and take together all the information of different fields. And so this is some characterization, I would say, which also is inherent in this scientific, well, what should I say, scientific to search for the laws which governs nature. They saw they have to divide, but also to combine. That's, well, I mean, at the moment, I do not know. You also use for social processes physical laws. I mean, everything was, it's called sociophysics. And one of a prominent colleague is Stauffer, for instance. And you can, and already Newton treated in economics people like atoms, or you have units, and you look how they interact and how they develop. But what I also want at this moment to say that the interaction of countries and human beings is not very good, in a very good shape developed, and I think because of wars. You could not, looking at the interaction in science and cooperation, gain much enough for our political interaction. And that's the drama in our century we just have to look at. But it's in some sense, I see it in a similar way.
Thank you. Some other questions? If it is not the case, let me thank the speaker again and thank you all the attendees of today's seminar. Next seminar will be in 1 month from now. It will be in the field of philology. One more, it will be in biology, and in January we'll have the seminar in mathematics. So different fields. And as usual, you are very welcome to attend our seminars. Thank you, Reinhard. All the best to you.
Thanks a lot for the talk.
Thank you for coming.